Okay, this is my second attempt at standard 1.1. For the second attempt, I decided to do 1.10, which says to consider these three quantum states. And then for part A, it asks us to find, for each state above, calculate the probabilities of spin component measurements along the x, y, and z axes. So before we can calculate probabilities, we need to make sure that each state is normalized. To normalize, we simply bring in a complex multiplicative factor c, and we can solve for it by using the normalization condition, where basically you take the inner product of each state with itself and set that equal to 1. So we do that, and then we set our complex multiplicative factor out here. We simply go through the steps, and when we solve for it, we see that we get c equals 1, which implies that the state is already normalized. We follow the same steps for state 2 and state 3, and we get that c equals 1 for both, so we realize that all of them are already normalized. So the next part is to calculate the probabilities. The book says we can find a probability that a measurement on an input state will yield a certain result an corresponding to the ket an. We're given the kets plus and minus for each of the axes in our book, so we can simply solve for the plus and minus x, y, and z axis probabilities. So, for the z-axis in the positive direction, to do this, to get the probability, you take the inner product of the direction with the state that you want, and you take the modulus, you square the modulus. So when we do that, we get for the eigenstate phi 1, we get a probability of measurement on the z-axis, positive z-axis is 16 over 25. For phi 2, we also get 16 over 25. Phi 3, we also get 16 over 25. And we see that for each one, we just follow the same steps. For spin down, we do the same thing, except we use the negative direction now. And when we do that, we get the probability for phi 1 is 9 over 25. And then similarly, same steps, we get that phi 2 and phi 3 also have probability in the negative z direction of 9 over 25. Continuing with this, we move on to the z-axis. So for spin plus on the z-axis, we do the same thing, except the ket for the x-axis is a little bit different. We have this right here instead. So for phi 1, we go through the steps, we get probability 1/2. Do the same thing for y2, except we're just replacing this phi 1 with phi 2, phi 3, and we get 1/2 for both of those probabilities. On the negative x-axis, do the same thing again, a little change in the negative x direction as well for the vector. Then we get a probability of 1/2. And again, same steps, except substituting in phi 2 and phi 3 here, we get probabilities of 1/2 for both phi 2 and phi 3 as well. On the positive y-axis, again, we do the same steps, except here we're plugging in the positive vector in the y direction, which has a little different because it has this I factor right here out front. And when we do probability for this, for phi 1, we get 49 over 50. Moving on, for phi 2, we go through the same steps, probability of 1 over 50. And for phi 3, same steps, we get a probability of 1 over 50. And then again, for the negative direction, it's the same thing, except you plug in the negative of y-axis direction. We get a probability of 1 over 50 for phi 1, probability of 49 over 50 for phi 2, and a probability of 49 over 50 for phi 1. Also, if you look back at the work, it's pretty simple to see. For each state, phi 1, phi 2, and phi 3, the probabilities along the z-axis for the negative and positive direction add up to 1, and you get the same case for the x-axis and the y-axis, where all the probabilities added up equal 1. This makes sense because if we're measuring along the axis, there should be a 100% chance that we find it somewhere on the axis. Alright, and then we have part B. Switch this over so you can see. There you go. Alright. For part B, it asks to use your results from part A to comment on the importance of the overall phase and of the relative phases of the quantum state vector. So, we can consider these two arbitrary states, A and B, where this, considering these two states, A and B, where we have this relative phase factor out here, and we don't have it for the state B. So here, just phi and beta correspond to quantum states, and x is a relative phase factor. These two states do not correspond to the same physical state and are not interchangeable. We saw in part A that a relative phase factor gave different probabilities. But if we have two quantum states with an overall phase factor, so it'd be like if B equaled this, and then we put parentheses around here, we would have where this factor commutes to both states. Those two quantum states would correspond to the same physical state. So essentially, what we have is relative phase factors are non-physical, whereas overall phase factors are physical. And that is it for problem 1.10.